Well, hi everyone, and greetings from Northern Michigan. This is Bob the Science Guy. Today, for Friday Science, we're going to do a video that I've wanted to do for some time, and that is, we're going to have a look at the lunar eclipses. So let's cue up the music and get going. Now, lunar eclipses was one of our first indications that the Earth was a sphere. The ancient Greeks observed that the moon was not part of the Earth, and surmised that when a lunar eclipse occurred, it was the shadow of the Earth being cast upon the moon. They noted that that shadow was round, and it was always round. The only geometric shape that would cause a consistently round shadow at all times of the year, in all positions of the sun, would be a sphere. So let's look at the geometry of a lunar eclipse. Now first, a quick disclaimer. This is not to scale. Now, the sun is out here, the Earth is here, and the moon is right here. Now, a lunar eclipse occurs when the Earth is located between the moon and the sun and falls within the shadow of the Earth. Now, as you can see, there are two components to our shadow of the Earth. We have a partial shade, which is called the Penumbra, and then we have an area of the shadow called the Umbra that is fully shaded from the light of the sun. Now, to give you a quick idea of the sizes of these shadows, the Umbra goes beyond the moon to 1.4 million kilometers from the surface of the Earth. The Umbra is about 2.6 times the diameter of the moon, and the Penumbra is approximately 4.6 times the diameter of the moon at the level of the moon's orbit. Now, it should be rather obvious that the only time that a lunar eclipse can occur is during a full moon, because that's when the alignment is such that we have the sun, then we have the Earth, and then we have the moon. Now, normally, in that situation, on the night side of the Earth, we would see a full moon. And as a result of that, a lunar eclipse can only occur during the time that we would normally have a full moon on the Earth. So the obvious question is, why do we have a full moon at all? Shouldn't the moon be eclipsed by the Earth every time it's in the position that we would normally see it to be full? Well, actually, there's a reason for that, and that is because the orbit of the moon is not on the same plane as the orbit of the Earth around the sun. It's tilted approximately 5 degrees. And as a result, when the moon's orbit is tilted up or tilted down, such as you see right here, we will see a full moon on Earth. It is only when the moon is directly behind the Earth relative to the sun that a lunar eclipse can occur, and that can only occur 2 times in the orbit of the moon. Now, if this yellow line is the plane of our orbit around the sun, and the gray line is the plane of the orbit of the moon around the Earth, as the orbit of the moon is higher than the orbit around the sun, we can get full moons. But as it comes down and crosses this plane, we have what's called a descending node. Then the moon's orbit is below the plane of the orbit of the Earth around the sun until we come up to this side, where it starts coming back up and crosses again at what we call the ascending node. These are the only 2 times that we can have a complete lunar eclipse. So for example, during the ascending node, if the sun was out in this direction, we could have a lunar eclipse. Likewise, during the descending node, if the sun was down here, we could have a lunar eclipse at the descending node. These occur during very specific times of the year. Now, as you can see, during the summer, we're in the descending node. And as you recall, the descending node is when the moon's orbit starts above the ecliptic and then descends down through the ecliptic and out the other side. These eclipses occur in the summer. So in August of 2016, we had what's called a penumbral eclipse, where just a little edge of the moon touched the penumbra of the Earth's shadow. August of 2017, we had a partial eclipse, where we had part of the moon actually touch the umbra, and the rest was in the penumbra. July of 2018, we had a total lunar eclipse. Now in the ascending node, which occurs in the winter, the moon is coming up. So you see here we have a penumbral eclipse, we have a total eclipse, have another total eclipse. I actually watched this one, it was pretty cool. And then we had another penumbral eclipse in January of this year. So you see, the basic idea is the descending node means that the orbit of the moon is coming down through the ecliptic, and the ascending node, the orbit of the moon, is coming up through the ecliptic. And this is, of course, viewed from the northern hemisphere. Now, one other thing that you may find of interest, if you look at the partial eclipses like this one right here, notice that the moon appears to be somewhat normal in coloration, but in a total eclipse, it tends to turn reddish. And sometimes we use an unofficial but rather common name of a blood moon for this. Now, why is that? The answer has to do with Rayleigh scattering. And we see examples of Rayleigh scattering all the time. Notice the red color of these clouds. The reason for that is as the sun sets and rises, the sunlight has to go through more of Earth's atmosphere than it does when it's at 12 noon. And as a result, there is scattering or absorption of the shorter frequencies of light, such as the blues. That leaves just the red light to get through and light up these objects, so our eye perceives that as the objects are turning red. The same thing happens with the moon. As the light comes around the rim of the Earth, it undergoes Rayleigh scattering, and the light that illuminates the moon, to a small extent, is a reddish color. Now, how long does a lunar eclipse last? Let's have a look back at this diagram. Now, right here is the moon. The width of the umbra at the level of the moon's orbit is approximately 9,000 kilometers. And that means that at most, it will take the moon 107 minutes to travel completely through the umbra. Now, the penumbra at the level of the moon's orbit is about 16,000 kilometers long. So at its maximum width, it will take the moon approximately 4 to 6 hours to travel completely from one end of the penumbra to the other. The moon's orbital speed is about 1 diameter of the moon per hour. Now, another factor that will affect the length of the lunar eclipse is where the moon is in its orbit. As you recall, the orbit of the moon is elliptical. It has an apogee and a perigee. At perigee, it is closest to the Earth and moves through the shadow faster. At apogee, when it is farthest away from the Earth, the shadow is the largest and the moon's orbital speed is the slowest, so the eclipse will last a little bit longer. But perhaps that needs a little more clarification. The penumbra is at its largest when the moon is farthest away at apogee. The umbra, which is the cone of darkness behind the Earth, is actually a little bit smaller. So the entire length of the eclipse will be a little bit longer, but the period of totality will be a little bit shorter. Whether or not this is offset by the slower orbital speed of the moon, to be honest with you, I haven't checked. That might be a good little bit of math to try and do. Now, there are 4 basic types of eclipses, and they're noted right here. A penumbral eclipse means that the moon passes through the penumbra of the Earth's shadow, but not the umbra. If it touches or goes through the umbra, it's either a partial eclipse or a total eclipse. And there's one more type of eclipse. It's called a selene-Helian eclipse or a horizontal eclipse. It only occurs when the moon is on the horizon of the Earth. And it's the only type of an eclipse where you can see both the moon and the sun in the sky at the same time. So how on earth could that possibly happen? Now, this is actually a very interesting phenomenon and has been used by certain people to try and prove that the Earth is not a sphere. Let's go see if we can explain it on a spherical Earth using things that we understand very well. Now, one thing that we have seen quite a bit of recently is something called refraction. This is the bending of light as it goes through the different layers of the atmosphere, and it can result in something called looming, where objects that are below the horizon appear to be loomed up above the horizon due to this bending of light. Now, as light bends like this, when we're observing it, we tend to make straight lines. So an object that is down here, but the light's bending up towards our eyes, will appear to us to be a little bit higher in the sky. And this is how the selene-Helian eclipse occurs. Let me show you. So here we are sitting right at the terminus line on the Earth, right at sunset or sunrise. The sun's out here, the moon's over here. Now, as we look out on the horizon, the moon, which is below the horizon, appears to be a little bit higher so that we can see it. Likewise, the sun is below the horizon, but because of this refraction and this bending, appears to be a little bit higher. We see the sun and the moon. However, the sun is below the rim of the Earth and the moon is below the rim of the Earth, and as a result, the shadow of the Earth is cast upon the moon. We see that shadow as the moon is loomed up. So the bottom half of the moon here will be in partial eclipse. And here's an example of that. As you can see, it's still daytime, so the sun is above the horizon behind us. But as we look out on the moon, it's in partial eclipse right here. Pretty cool, isn't it? And again, the reason that this occurred is this is an illusion of where the moon actually is. It's really a little bit lower. Likewise, behind us, the sun is lower than it appears to us as we turn around and look at it. So this portion of the moon right here is within the shadow of the Earth. So those are the mechanisms, the geometry, and the different types of eclipses. I hope that you enjoyed it and found it as interesting as I did. Now, in our next episode, we're going to talk about solar eclipses, including tackling the famous question of how can the shadow of the moon move from west to east across the surface of the rotating Earth? So I hope you'll join me for that. This is Bob the Science Guy signing out from Northern Michigan. Thank you very much for stopping by and for your support of this channel. Make sure you hit that little like and subscribe button down there. I'd really like to have you all on Team Bob. We'll see you again soon. Take care.
Mama, please make them hear me, or I can't teach them anymore. This rabbit hole's too deep for me. Feel my brain getting real sore. Bob the Science Guy. Bob the Science Guy.